Welcome to this short presentation on 5G and FAPI 1.0 release. My name is Ganesh Envaraman from Redisys, and with me I have Andre from Qualcomm. And the key contributors of this specification are Geo, Redisys, Qualcomm, Picocom, Microchip, Airspan, and other companies. This first release enables a disaggregated RAN architecture for the 5G small cells, which gives the abstraction and interoperability for system vendors, software vendors, and the hardware vendors by enabling FAPI across a non-ideal backhaul. And with this non-ideal backhaul based FAPI, we have a converged approach towards virtualization and a scalable ecosystem, full interoperability among all the vendors, and the benefits of centralization. A quick overview of the framework of NFAPI. In the disaggregated architecture of 3GPP, we have the CU and DU, and in small cell forum, we use this terminology of SDU and SRU. We will explain those terminology in a later slide. The CU and DU connect to the RU over a 5G NFAPI link. The 5G NFAPI adds a network transport wrapper around the 5G FAPI, and the 5G FAPI was published last year. It's a Phi 2 MAC API. This is option 6 based solution in detail, and you have an SCU, which is the centralized unit, the PDCP and RRC, and the RLC and MAC in the SDU. They talk to the SRU over an option 6 split NFAPI interface, and the SRU consists of both the PHY and the radio, and an SRU can have multiple PHY instances as well. In the next slide, we are talking about the basic interfaces of the base 5G FAPI. We have interfaces P4, P5, P7, and P19. P5 is the configuration and control interface. P7 is the data transfer interface, and P19 is a special interface, which is essentially for the control of front-end unit, which is part of the radio system in the SRU. The other interface which we have here is the P4, which is the network monitoring mode or sound-like interface, and that does the network monitoring functions. These FAPI interfaces have an equivalent mapping in NFAPI. On the left side, if you see, the 5G FAPI interfaces are shown, which is in this slide we are showing only the P5 and P7. And the P5 and P7 interfaces exist between the L2 and L1 layers. And on the right side, if you see, we show how this is transferred over the network through an NFAPI interface. Essentially, you see a translation happening between the FAPI to NFAPI interface at the sender end and an NFAPI to FAPI translation at the receiver end. The NFAPI messages are all defined, which we'll cover in the later slides. And the P5, P7 essentially now get transported over a network interface. The key interfaces of interest in the first release, P5 and P7, we'll have a quick look at those interfaces. The P5 procedures are essentially the procedures which configure and control the PNFs or the SRUs and the 5 instances within a PNF. And if you look at the stack diagram here, the L2 layer shown as a VNF can do all the control and configuration procedures towards a PNF, which is a SRU, or a SCTP transport based interface called P5, and the messages are defined in the NFAPI specification. The SCTP payload protocol identifier for 5G NFAPI is to be assigned with INE. Small cell forum will get this assigned, and with that, this P5 procedure provides reliable delivery of signaling messages over an SCTP link. And the next interface is the P7 interface, and in P7 procedures we provide the FISync, delay management, and the APIs for uplink and downlink data transfer. If you look at the stack diagram here, the layer 2 sends the data over an UDP interface. Here it's a fast connectionless protocol with the ability to retransmit, and UDP is the choice of the protocol here. and data can be sent and received over this UDP interface in a very fast and efficient manner. And the P7 interface also contains the procedures to align slot timing and jitter between the VNF and the FAI instances. So with this level of detail, I will now turn it over to Andre for giving you a deeper view of all the procedures.
Thank you, Ganesh. The Enthappy framework is evolved and optimized for 5G NR, mostly for latency, as well as for inclusion of the 5G FAPI protocol. The 5G FAPI protocol, described in SCF 222, was released in March 2020. The protocol supports the 3GPP release 15. As a consequence, the Enthappy protocol, the 5G Enthappy protocol, also supports the 3GPP release 15. There are three types of 5G Enthappy messages. Dedicated Enthappy messages are defined only in Enthappy. They mostly target the physical network function, PNF. As a consequence, most of the dedicated Enthappy messages start with PNF underscore, but there are other messages as well. Transparent messages are messages that contain FAPI and are carried transparently by Enthappy without additional messages or information. For these, Enthappy is just a transport protocol. And finally, combined messages also carry Enthappy messages, but in addition, they also carry TLVs, type, length, value, fields which contain other information in addition to the 5G FAPI message. A 5G FAPI message contains a header and a body. The header, the Enthappy header, indicates the ability to segment as well as the ability to combine multiple messages, since one header can contain a segment length, a segment number. As a consequence, each segment has its own header. The last segment has the more field turned off. So it indicates that it's the last segment of the message. From one Enthappy message to the next, the sequence number increases to indicate that a new Enthappy message is meant. Messages may contain the transmit timestamp, and they have to do so for messages involved in the delay management, such the P7 slot level messages. After the Enthappy header, follow the Enthappy messages themselves, and as I mentioned, there could be multiple Enthappy messages in one under one Enthappy header. In this particular case, a single Enthappy message is illustrated, and the message has its own header. That header has a field called reserved, which is meant for compatibility with FAPI. Has a FAI ID, indicated the physical instance, the FAI instance that originates or terminates the message, and it may be 0 if the message is not intended for a FAI instance. It could be for the PNF. Finally, a message ID and a length ID. After this starts the 5G Enthappy message body. Now, the most complete type of Enthappy message is a combined Enthappy message that, as I mentioned before, contains both Enthappy messages, or at least one of them, as well as additional information. As described before, this starts with an Enthappy header, followed by, for the message itself, the Enthappy message header. There could be multiple messages, so then each one would have its own header under one Enthappy packet. And as you see here, the header is followed by the message body, and the message body contains an error code as well as a number of TLVs. The message body is followed by a few TLVs, the first one of which is the Enthappy P7 PNF address, and it's presented as a TLV, as a tag length value combination. And then the following one is the PNF port, P7 PNF port, again a TLV combination. And finally, there's yet another TLV which transparently contains the 5B FAPI message body. In this particular case, it's the 5G FAPI param response. And again, it's a TLV. Now, the FAPI messages can be extracted from the NFAPI packet as follows. After the NFAPI header, follow the various NFAPI messages in the packet. So illustrated here is the extraction of the first NFAPI message. As you notice, the header, the reserve field maps to a number of file messages, and it's specified as 1 in NFAPI. That would be for aggregation level 1 for FAPI. If the message body happens to contain a FAPI message, then the extraction is exact. If it's an NFAPI message, then that extraction does not map to a FAPI message, but would contain an NFAPI message. And then the handle, message length, fields of the header, they are the same as in FAPI. Similarly, a second NFAPI message can be contained, and the extraction for it would proceed along the same lines. The reserve field always 1 in NFAPI. In this particular case, physical ID, file ID instance 2 is targeted, or originating message ID length, and then finally the body. There are PNF procedures that have a state machine similar to the FI state machines in FAPI. The idle, configured, and running state, they have APIs, and FAPI APIs that trigger a transition. So from PNF idle to PNF configured, you trigger a transition via PNF config that request. Then from PNF configured to PNF running, you trigger a transition via PNF start that request. Then you may return back to configured via PNF stop that request. In PNF idle, you may pull the capabilities and other parameters of the PNF via the PNF param that request message. And in PNF configured, you may configure the PNF via PNF config that request message. The FI instances, each one of them has an idle, configured, and running states. And the idle state to configured state is triggered via configured request, configured to running via start at request. These are all FAPI messages for the FI side. And then returning back to configured via the stop that request message, again, FAPI side. And then you may also use the FAPI messages inside an NFAPI encapsulation, param that request in idle mode, and config that request in configured state. The running state for FI instances may also undergo a downlink node sync procedure. For the PNF initialization, that one runs deep in the VNF, which serves the role in this particular case of the DU, and the PNF, which serves the role of the RU. VNF stands for virtual network function, PNF stands for physical network function. The first procedure is the PNF param procedure, then followed by the PNF config procedure to bring the PNF from idle to configured state, and finally the PNF start procedure to bring the PNF from configured to running state. After the PNF is in running state, then the FI undergoes its own procedures, param, config, start, to move the FI to its own in idle, configured, and running states. And finally, the node sync procedure maintains delay management between the VNF and the FI, so the VNF can appropriately target slot-based messages to the FI. Each of the FIs has to undergo a FI initialization procedure. The delay management procedure mentioned earlier consists of the node sync procedure and the timing info reporting. The node sync procedure has a downlink node sync followed by an uplink node sync. The downlink node sync carries the timestamp of the downlink node sync transmission at the VNF, and in the first case, 0 indicates that there's no intention to shift the FI slot timeline. Upon receiving the downlink node sync message, the FI records the receiving time as timestamp T2, and it reports T1, T2, and also T3, which is the sending time from the FI of the uplink node sync, it reports these 3 timestamps in the uplink node sync message back to the VNF. So at this point, the VNF has all the information needed to compute the latency. Additionally, the VNF may advance or regress the phi slot timeline by indicating a non-zero parameter after T1. In the second case here, it indicates an advancement of +8 slots. So for instance, the message arrives at a phi after time SFN 12 slot 9. So normally the phi would then proceed to SFN 13 slot 0, but because of the +8 instead, it follows with a SFN 13 slot 0 +8, which is 8, after the reception of the downlink node sync message. And then finally, it replies to this message with a normal uplink node sync with the timestamps T1, T2, T3, representing the arrival of the downlink node sync procedure, the T1 from that procedure, as well as the sending of the new uplink node sync message. Afterwards, the VNF maintains awareness of the receive window on the phi side by tracking the timing info reports from the phi side back to the VNF. In this particular case, we illustrate a case where downlink Enthappy message, downlink_TTI, is received at the phi after its intended receive window. In this particular case, it's targeted towards SFN 14 slot 4, but it is received after the occurrence of SFN 14 slot 4 at the phi. As a consequence, the phi triggers a timing info report back to the VNF to let the VNF know the late arrival of the downlink TTI message. So then the VNF can take appropriate action to make sure that the receive window is sized appropriately, as well as targeted appropriately, as well as the transmit window at the VNF side. The timing info report can also be periodic, not just event triggered, based on configuration.
Thank you so much, Andre. And with the detailed overview of the FAPI procedures covered so far, we would also like to talk about what is planned for the next releases. As further enhancements, we are also looking at some of the robustness enhancements in the FAPI framework. There will be some transport level enhancements for P7 especially. We plan to add the FAPI P19 interface support, which is the front-end control interface, and the P4 network monitoring mode interface. P4 interface will also be added in the next releases. As part of ecosystem support, we also are looking at providing the management models, looking at the transport network requirements for FAPI to work seamlessly in deployments. The synchronization and timing design, which is a challenging topic when it comes to deployment, that will be covered as a white paper from sponsor firm. And we are also looking at test and measurement vendor support to enable FAPI in its full form. And that's something that ACF sponsor forum will be working on constantly. So that brings us to the end of this whole presentation. Thank you for listening in. And for further information, you can download the FAPI specification and our guide from our website here. Thank you so much. Thanks for listening.